Okay, so we are group 22. Here we are presenting our project about CT segmentation with convolutional neural networks. Next page. So first we are start with a brief introduction of what this project is about, and then we will describe the data set we are using. After that, we'll describe the very famous UNet architecture, which consists of a series of convolutional neural networks, which is very effective on segmenting images. And lastly, we will present you some of our own results. Next page, please. So CT stands for computed tomography. It provides very detailed cross-sectional views for internal anatomical structures, and this is a very important technology in today's medical treatments. However, interpreting the image is very time costly and also prone to variability among experts and challenging in some very subtle conditions. So image segmentation optimization is a very fundamental step for quick, robust, and also effective step for promoting the efficiency of such processes. Okay, please, next page.
So for our experiments, we're taking the KIDS-19 dataset, which is an open source dataset for kidney tumors. We're sampling randomly like 100 CT volumes out of the entire open source dataset, and we define our problem to be a 2D kidney segmentation problem. Therefore, we're taking axial slices of a total number of around 22K, and we have a brief slice count per volume set over here. And because of the nature of nifty data format, it is super slow to load it into the memory and then process it, and it takes extremely large volume of the RAM. Therefore, I performed a pre-cached calculation to transform the original nifty format into NumPy arrays, and I standardized it to be a uniform 512 by 512 dimension. And therefore, I can pre-cache all the arrays into the disk and then use this memory mapped arrays for faster I/O. So we performed some data pre-processing with HU clipping, clipped by -200 and 300 before normalization. And we also perform normalization to ensure per case consistency by calculating the mean and standard deviation. And since we define our problem to be a 2D kidney segmentation, and the original dataset was a multi-label dataset, so we pair only the kidney mask and the background as our mask pairing. So could you go back to the previous slides? And because the dataset is consisting of a lot of slices, which most of them do not have a liver within the slice. So I also performed the data balancing to ensure that our training set we use an equal number of slices with only backgrounds versus where there are liver present in the slice.
Yeah, so here we start introducing what is about with the UNet architecture. So the reason this is called UNet is because it is usually drawn in such a U shape. So the architecture first starts from reading the input data. In our case, these are 512 times 512 in spatial images in spatial size. And then the first half of this architecture, which is the left half, is going down. So this part is called the encoder, which what it does is called down sampling. So we can see the image size are going smaller and smaller. And then when it goes to the bottom of the architecture, this part is called the bottleneck. And after this part, the images are again enlarged until the last step, the output is the same size of as the input. Next page, please. How it works. So the encoder, which is the left half of the architecture, this part progressively downsamples the image using convolution pooling layers. This is used to capture the high level semantics features. And then the bottleneck, it's actually force the data to only pass through the most essential information of the images. And after that, the decoder upsamples those features back to the original resolution. That's why this part, the images again become bigger and bigger. The structures allows the network to understand both the context and local detail, essential for precision boundary detection segmentation. So the very one key innovation about UNet is that it skip connections between matching layers in the encoder and decoder. So this helps the network recover fine-grained spatial information that will otherwise be lost during the downsampling. So this is actually indicating the gray arrows in the figure in the last slide. Next page, please.
So our implementation was briefly covered in the previous slides, and we use because the input is an converted arrays from the Nifty format, so the input is a single channel Excel slice, and we use a double conv per stage and downsample the width, the channels, expanding the channels actually from 32 to 256. And the double conv components is composed of two convolutional layers, two normalization, two ReLU, and we downsample using a 2x2 with a stride of two downsampling convolution layer. And then by the bottleneck, it reaches a channel of 512. Next slide, please. And afterwards, we use the decoder by using bilinear upsampling, and with all the red arrows representing the bilinear upsampling. And finally, after all the decoder stage, it comes back to a head with it, which is a final one by one convolution layer, and then it is passed to output a two digits output. So in the end, we apply a sigmoid to make it produce a meaningful prediction on segmentation. The training loss we adapt in our experiments is dice plus binary entropy loss, which is very common for segmentation tasks. So this is our entire structure of the UNet that we actually implemented. And the training results were pretty typical. We see a very smooth and steady decay in the training loss and a steady, well, sort of steady improvements of the validation dice. The best validation dice of all epochs we reached is 0.7283, and the test dice score is slightly lower, but it reaches 0.62.
And next, I will introduce the results and the sample outputs. This slide shows how our convolutional neural network accurately segment the kidneys from CT scans, closely matching the ground truth annotations. And this example shows the convolutional neural network can accurately identify kidney regions, even in complex annotational variations. This slide illustrates a challenging case where the convolutional neural network partially over segments the kidney region, highlighting areas for further model refinement. And this case shows a missed segmentation where the CNN fails to detect the kidney emphasizing the challenge of low contrast region in CT imaging. To summarize, our UNet model has limited capacity and loses 3D context, suggesting improved performance with larger 3D UNet trained on a richer dataset. Thank you very much for the attention.